Greetings, everyone. Time to talk about an efficient way to graph functions that we will use a lot in many different subjects of math. What we're going to do is we're going to talk about some basic shapes of simple one-term functions. We call them parent functions. And then I'm going to show you a list of little rules, a schematic, if you will, of how we can change those equations one piece at a time to make graphs that we want, or vice versa. If we see an equation that we can pick apart, we can tell how the graph has been changed from the basic parent function. So let's start with these basic shapes, okay? Some of these you may recognize and some maybe not, but let's find out, right? Y equals x is your basic line that goes through the origin. Y equals x squared is your basic parabola that also goes through the origin and is facing upward. Y equals x to the third is your basic cubic that goes through the origin after flattening out in the middle. It's literally what we call a saddle point. It gets horizontal for one point right there in the middle, right? And then it's teaming up to infinity and negative infinity on either side. Okay? The absolute value function is basically the same as the y equals x linear function, except the negative side has been broken to face upwards. And since the line typically makes a 45-degree angle when it's not, rotated or tilted by a slope, the whole V shape here makes a 90-degree angle between the two pieces there. So the absolute value shape is this V shape, because the absolute value wants to make everything positive, unless you do other changes to it. Okay, the square root function is literally the same graph as the square function here. They're both parabolas, but this parabola, since the relationship is reversed, is a right-sided parabola. And if you think about it for a second, a right-sided parabola wouldn't be in the category of functions that passes that vertical line test. So what had to happen was we had to cut off the bottom half of it. And so you're only getting the top half of a sideways parabola there, okay? Also, I'm sure you're familiar with a lot of times when you have a square root, you usually get that plus and minus going on with it, right? Well, that's where the cutoff happens. Notice it's not plus or minus, it's just the positive one, which is why I'm only getting the top half here. The cube root function is literally the same graph as the cube function, right? But it's sideways instead of vertical, right? It's going left to right instead of a more down to up sort of shape. But if you were to pick this shape up and lay it on top of them, they would be exactly the same point for point, okay? So these two shapes are the same. And the relationship, by the way, between these two being the same and these two being the same should make sense to you. Those are opposite operations of each other, right? Square is opposite of square root. Cube is opposite of cube root. It's basically the same relationship, just in a different organizational relationship there, right? Different organizational direction, paradigm, if you will. Okay, then you have the two basic rational functions. The reciprocal function, 1 over x, I tend to call this one the baseball function, just because look at the shape. It splits between the first and third quadrants here, and it looks like the crosshatch on a baseball. I've heard other math teachers also call it the butterfly function. I'm a little bit more like, let's call it the baseball function, right? Okay. And then you have the reciprocal square function, 1 over x squared. I call this one the volcano function. I think that one's kind of obvious, right? It hugs the y-axis and never crosses the x-axis. There, okay? So what we're going to do in a moment is I'm going to show you the schemes that we can use to change the equations of these on a basic level and how that affects the graphs. And so when you approach an equation and have to graph it, you can do a real quick graph, okay? I want you to keep in mind that the graphs that we do in this lecture for this section are more meant to be a speedy attempt at understanding just the overall idea of what the graph is doing. It's not meant to be 100% accurate. It is meant to save you time when you're doing other applications and you just need an understanding of, okay, yeah, I understand why it's doing that because the shape is this, or it's located over here, whatever, okay? So the idea here is fast graphing. I usually call them 80% graphs instead of 100% graphs, right? Because some of it may be a little bit off accurate. As you can see, like I had to redraw a couple of these, right? My points aren't going to be 100%, right? The distance here and here is supposed to be equal, and it may not be in my drawing just because I'm just throwing it up there without graphing a bunch of little points, okay? The first category that we want to talk about is called translation, okay? Don't get that word confused with transformation. Transformation is a generic word for all of the actions that we can take in moving a function around. A translation is when we shift it without changing the orientation whatsoever and without changing the shape whatsoever. It's literally picking up the shape and just putting it down somewhere else with a new center, okay? And that's the key to most of these, by the way. I hope you noticed in the graphs before that they each had a centering, and pretty much all of them, in fact every single one of them, was centered on the origin 0, 0. Okay? Now I say centered, of course the square root function has the starting point there, right, and it goes off at the origin, but you get my point. The 0, 0 point on those original functions is the one that I will be shifting first, and then I draw the rest of the shape around that. Okay, so now let's talk about how we can read what shift we're supposed to be doing here. Okay, so whenever we're adding and subtracting a number inside of a function, okay, that's going to be some sort of a movement, either up, down, or left or right. And you can have a combination of a vertical with a horizontal movement. Okay, a right with a left doesn't make sense, but a right with a down can happen. Okay, so if you see the number added or subtracted on the inside of the function, that would be inside of a set of parentheses, under a radical, inside of the absolute value bars, but it's inside and it's directly being added to the x variable itself. Okay, something that affects x directly is going to have a horizontal effect. Okay, and also, by the way, most things that affect x directly are happening before the function gets its turn with the input value. So all of the things that are inside like this are going to have sort of an opposite logic feel to them. For example, on the inside, when I add a number, it's actually shifting to the left. And when I subtract a number, it's actually going to shift you to the right. And that's because, again, you're adding and subtracting directly to the x variable, which is more like shifting the axis itself. Okay? So your graph is there and I'm shifting the axis away from it. We just tend not to think that way because our minds like to think in terms of outputs, right? The graph itself. So this is what your perspective is going to be. If there's an added number in there, the graph will seem to move to the left, and if there's a subtracted number on the inside, it will seem to move to the right. Okay? At any point on the inside portion, right, I have this extra little side trick that you can do to check yourself, and that is whatever value zeroes out the entire inside calculation is the new centering point of that function. It used to be at 0, 0, and whatever zeroes out the inside portion has that same role as 0, 0 used to. Okay, so I'll show you when we're graphing a couple of them that you can do that also. Vice versa, anything on the outside of the function, so that would be something on the outside of parentheses, outside of the radical hood, outside of the absolute value bars, not inside of the fraction, whatever. Okay, and if you add, you get a shift up. If you subtract, you get a shift down. That should feel more like it's making sense, right? Because I'm adding to the outside of the function, it'll make the whole function go up. If I'm subtracting from the outside of the function, it'll make the whole thing go down. Okay, so if you're looking for which way to shift, you have to determine if the number's being added and subtracted on the inside or the outside, and then whether it's addition or subtraction for each one. Okay? So let's go through all of these and let's just identify the shifts, and then we'll go through and graph them. Okay? So right here, y equals x plus 3 quantity squared. The squared is the parent function here. That's the function that we're worried about that's going to give us our shape. Okay? So that's what I'm looking for. I'm thinking to myself, oh, it's a square function. It's going to be a parabola, right? And it's been added on the inside, right? Added on the inside by 3. So this piece right here is going to be a shift left. Okay? How about this one? Square root of x, and then there's a minus 1 on the outside. Well, I'm subtracting, and it's outside of the radical. So this minus 1 right here is going to be a shift down. Okay? As I was saying before, you can have a combination in your shifts. See, notice I have a 2 added on the inside and a 4 added on the outside. So for this particular problem, this 2 right here is going to be a shift left, and this plus 4 right here is going to be a shift up. Okay? And then over here I've got one of the rational functions, right? Where the inside and the outside have to do with the placement in the fraction itself. The original function was 1 over x, right? That's the original. The minus 5 is in the denominator with the x. So that's my horizontal change. And then the plus 2 is outside of the fraction. So there's inside, there's outside. This minus 5 right here is a shift to the right. And this plus 2 right here is a shift up. Okay? So now let's go back around and graph all of these functions. Okay? So what I'm going to do is I'm just going to put down a really raw grid. I don't need a lot of numbers. I just need enough to get the location of these graphs. Okay? So it's been shifted left by 3. So it used to be here at the origin. I'm going to go 1, 2, 3 to the left, like so. And then I'm going to remember to myself, okay, what shape was that? That's x squared. That's the parabola. So it'd be just like that. Okay? Notice I didn't have to scale anything on my y-axis because I'm not really focusing on that. I'm really just focusing on really 3 things. And this is also whenever I'm grading one of these and whenever I'm talking to someone about this, the main point between these things is, does it have the right direction? It's up, that's correct, right? Does it have the right location, right? That's the location is over here. And does it have the right shape, right? The parabola, the basic parabola, and it hasn't been stretched or twisted in any kind of way, right? So we're worried about shape, location, orientation. That's the 3. Next, square root of x minus 1. So I'll put my grid up here. And I've been shifting down by 1. So from the center point here at the origin, I shift down 1. And then I want to graph the square root function, which basically just has a starting point here and just does the top half of the sideways parabola that way. So notice it's just been shifted down by 1 there. Okay? Okay, on this one, I've got that absolute value function, which is the V shape, right? So I'm going to draw my basic grid here. It's not even a grid, right? Just my basic setup for my axes, x and y axes. It's been shifted 2 to the left, so I'll do 2 to the left here. And it's been shifted up 4. So something like that. and then it is the absolute value shape unchanged, so it should be the V shape with a 90-degree angle, and it's been shifted left 2 and up 4. So that's right here is my new center point, okay? And then my V shape is going to go this way, like this, okay? Lastly, I've got the rational function here. It was the 1 over x, which remember is the baseball function, right? This one, I need a little bit more guidance though. I'm going to put my x and y axes down as usual. Okay? So I've got my x and y axes, and it was shifted right 5 and up 2. Okay? So that's the center point right here, right? However, think about that baseball function shape for a second, or if you want, go rewind and come back to this moment. Did you do it? I guess you did do it, right? Remember, it doesn't actually go through the center there. It's actually the shape, what we call a hyperbola. It has the piece going down this way and has the piece going down this way. It's the baseball shape, right? So it's going to hug around this way and up around this way. And I don't have a good way to graph that when I'm not actually using the x and y axis as my centering, right? Because before I had the x and y axis to sort of hug the lines, and that helped me out when I was graphing it the first time. This time, to get my assistance, what I do is I pretend I have a new set of axes. It's not the actual x and y axis, but what it is I can use the line y equals 2, right? Because remember, that's a horizontal line. The horizontal line, y equals 2. And the vertical line, x equals 5. And their center is the new center of my graph, okay? So then all I have to do is hug these like I'm supposed to, like this, and like this. And then I've got that graph shifted appropriately. Okay? The other thing is, remember the trick I was telling you about? Whatever zeroes out the inside is the new center x. Notice that's absolutely true. -3 plus 3 is 0. It's centered on -3. Okay? This one isn't shifted left or right. So 0 is still my center at x equals 0. -2 would zero this one out. Again, -2 is my center x value, right? And then 5 would zero out this bottom. And side note, 5 is not in the domain of this function, right? Because division by 0. Notice that's absolutely true. X equals 5 is the coordinate of this line right here. And it does hug that line, but never actually touches it, okay? And we'll talk more about those kind of lines, asymptotes, in end of chapter 3. The next category that we need to talk about is reflection. And really, this is sort of just an on and off type of situation. You either have the reflection or you don't. And the only reflections that we truly focus on are the ones that go around an axis. We don't reflect typically across lines that are way off center, or off to the left, or to the right, or up, down, whatever. We typically just say it's reflected across the x-axis or across the y-axis. And that's because they're very simple actions that occur a lot because they come from applying a negative, okay? And we apply negatives to functions and to variables all the time. And basically what that's doing is some sort of reflection across an axis. All right, so if the negative occurs on the inside, now mind you, it has to be inside and it has to be on the variable x. Okay, that's important. It can't just be a negative already attached to a number unless that's multiplied to x in some sort of way. If it was x minus a number, of course, that negative is not a reflection. It needs to be a negative that's somehow being applied directly to the value of x. Okay? In that case, you get your horizontal reflection, and that will be a horizontal reflection across the y-axis. So wherever your function is, y-axis is now the center, and it's just going to reflect horizontally with the y-axis as the center. If you have the particular negative on the outside of your function, then it does the same thing but vertically across the x-axis. Wherever your function is, it will simply do a up and down vertical flip like that with the x-axis as the center. Okay? So here's some examples. Notice if I put the negative on the inside of the square root, and wait, don't freak out. I thought we couldn't have negatives in square roots. We don't, because those would be imaginary. So imagine what would happen. The only way for this to work is that x can have negative values, and therefore it would be negative, negative, right? So notice exactly what happened. If I put a negative on the inside, I get a horizontal reflection. And instead of being on the positive side, now it's on the negative side. So it's getting a double negative when you plug in an x, okay? Simply putting that negative on the inside, make it turn to the left instead of the right, okay? With the y-axis as the center. Notice if you have a shape that is already an even function, it's symmetric on the y-axis. If you put the negative on the inside of absolute value, for example, I still get the same V shape because it was the V shape before, right? And if you flip it horizontally, it's still that exact same V shape. Some examples of some vertical reflections. If the negative is outside of the radical, notice you get the bottom half instead of the top half, right? It was reflected to the bottom side because I'm just making all of my y values the opposite of what they were before. Okay? Same thing here. If I have a negative outside of my x squared, it would normally be a parabola facing up. So that makes it vertically reflect to being a parabola facing down now. Okay? Let's get some mixture examples here. I have some stuff that has translations and reflections riddled throughout. Let's go through and pick apart the pieces first, and then let's get some practice drawing them. Okay? So notice that the only thing that's basic on this one should be the x and the cube, right? X cubed is the parent basic function here. Everything else in there is an individual little piece that I can pick apart and name as some sort of action. Okay? So the +1 being on the outside is a shift up. The +2 being on the inside is a shift left. And this negative being multiplied on the outside is a vertical reflection, right? This kind. And of course, the way this thing is written out, with the negative on the outside of the parentheses and things like that, you want to do your vertical reflections and your horizontal reflections first in pretty much every case, unless there's parentheses changing what's going on, okay? So you would do your vertical reflection first, and we'll do that graph in a second, right? Then do your translations. Okay, now this one is a trick question. Somebody is seeing if you're paying attention here and if you're using that extra little check that I showed you in the last scene. Let's pick it apart. Okay? This is a +3. It's being added on the outside. So this is a shift up. This is a negative being multiplied to the function, right? The negative is not attached to the 3. This is a vertical reflection. Inside, it is a +4. Don't let that fool you. The fact that there's a negative floating on the x has switched up everything on the inside. It gives an opposite of an opposite logic, basically. Okay? And you need to just take a step back for a second and think. What number makes this 0 on the inside? What zeroes out the whole thing? In other words, 4 minus x equals 0 would give me what answer for x? Notice if I solve that, I get x equals 4. So that must be my new center value. And notice 4 is on the positive side. It's a shift to the right. So even though this is a positive 4, because of the way this negative is attached to the x here, causing a reflection, this 4 is actually a shift to the right. Even though typically a plus 4 would be a shift to the left. Okay? These rules that I'm showing you are not hard, fast, all the time, 100% things. You need to also use a little bit of graphing and algebra sense. Okay? You need to look at what's really happening and where is my new zero center. Okay? And then, of course, this negative is actually on the x. So this negative right here is telling me that I have a horizontal reflection. Okay? So that one had a lot of different little pieces to it. Right here, I've got a vertical reflection, right? Because the negative is on the outside. It's not inside with the x. This negative is out here. So that is a vertical reflection on the negative right here. The -2 here is on the inside. That's normal, shift to the right. And the 5 right here is on the outside and it's added. So that is also a shift up. On this guy right here, you need to be a little more careful again because I'm seeing some parentheses, which remember, parentheses change the order of things, right? One way you could approach this is I could go ahead and just distribute that negative, okay? So one way of looking at this is that it's negative cube root x plus 2 plus 1. And that's probably the easier way to approach this one since it was such an easy distributive property and didn't really have to do a lot of simplifying, okay? But let's look at it from this standpoint for a second. If I have a function like the cube root here, the plus 2 on the inside is going to be a shift left. That's still a shift left. That doesn't change, okay? So no matter what, the plus 2 here is going to shift me to the left, right? Either way. But this -1 right here, if you look at just inside of the parentheses, should be a shift down, okay? So I would have my graph and I would shift it down. But then immediately, because of the parentheses, the next thing to happen to the whole thing is this vertical reflection right here, this negative. And by the way, that's the same here and here. It's going to be a vertical reflection either way, right? This negative right here is a vertical reflection. So is this one. However, the vertical reflection on this first guy here happens after the shift down. So it shifts down, but then my center line has been moved, but I still have to reflect on the x-axis. So if I shift it down, I have to do this, which actually converts it into a shift up by the end. Which notice that's exactly what the math is telling you. You should shift up and have the reflection. Okay? So this way with the parentheses, it's telling you, oh, we shifted down, but then we immediately reflected the whole thing across the axis. Okay? So that gives you a weird gap that reflects with it. Okay? So the gap normally would be a shift down, and then it gets reflected, and so that gap becomes a shift up instead because of the order in which these things were worked. That's why it's so much easier to go ahead and get rid of as many parentheses as possible, right? After I distribute it and you can look at this, you can tell right away, oh yeah, this is a shift up right here because it's independent, right? So it's that piece over there. So it'll be easier to graph that one. Okay, so let's graph. Right here on this one, I'll put my axes up. And I can see that I need some marks, 1 up and 2 left, so that I have a new center right here, right? That's my new center. But before I actually do the shifts themselves, I have to vertically reflect. Okay, well, which shape was x to the third power, right? We need to think about that. The shape used to be like this. The basic cubic looked like that. Kind of flattens out in the middle. If I vertically reflect that, right, the piece is up, the piece is down, flip it like this, it'd be vertically done like this. So now the left side is up and the right side is down. Okay, so it has to go through this center point right here. Okay, but it's going to come from this upward direction. It's going to flatten out, and then it's going to go in the downward direction like this. Ew, that's not spaced well. I know I know we said we don't really care too much about the actual accuracy, but I'm a little picky for myself. It should be more like that. It does eventually cross the axis, though. Okay. All right. So I have the vertical reflection on that one. Let's graph this doozy right here. Let's start with marking my shifts. I have to go 3 up. Okay? I have to go 4 to the right. My new center is here. And it's a square root function. But the square root function normally goes this way, yeah? It has been vertically and horizontally reflected before I shift it. Okay, so normally it would be here at the center. It's been horizontally reflected, so it's going to point to the left, and it's been vertically reflected. It's both. So it's going to shift down and left. So then the actual graph is going to look like this. Like that. Okay? Okay. Now, of course, I could be off on my intercepts there and stuff like that. Again, I'm not too worried about that. As long as you're getting the shape, the orientation, and the location of this. If you want more accuracy, you have to start plugging in points. And that's fine. It just depends on your application. If you need more accuracy, this is a good place to start in your mind. You'd be like thinking, oh yeah, I know which way that one should be facing, and then let me just throw in a couple of intercepts or something like that. For other versions of this particular thing, you may want to do that. Here, I'm speed graphing, right? I'm just trying to get the right shape, the right orientation, the right generic center location, okay? So here we go with another one of these rationals. Remember, these don't go through the actual center point. I need my guidelines on this one. I'm going to start with my X and Y axis. Okay. I got to go up 5. And remember, when I do that, what I'm actually going to do is put a guideline here. My guideline is the line y equals 5. I'm shifting 2 to the right. So 1, 2 to the right. And I'm going to put another guideline there at x equals 2. Yeah. Let me see. Let me stretch this one out just a bit more. Okay. Then it has a vertical reflection. So remember, before I actually do the shifting, in my mind I have to remember that my shape is going to change slightly. It's 1 over x squared, which was the volcano function. Normally it would be doing this, but it has a vertical reflection. So now it's going to be doing this. It's going to go downward, and then it's getting shifted. So it gets reflected, and then it gets shifted here. So this is what I'm going to do. I'm going to hug it into this so that it hugs these lines. Same thing here. Like so. Okay? Lastly, we're going to graph this cube root right here. So we need our x and y axes. I need to shift up 1 and left 2. So here's my new center point. It has a vertical reflection. Now let's think for a second. What shape was the cube root? It was the same as the cubic, except instead of vertical, it was horizontal, right? So the shape that I'm looking at for this one typically would have done something like this. That's the shape that it would have started out as, but it's been given a vertical reflection, right? So instead of going this way, it's going to flip, and it's going to start high at the left and go low to the right. So something like that. Okay? The last category that we need to talk about is whenever you have a stretch or compress version of your graph, and that basically just changes the shape a little bit. Sometimes in geometry, an action like this is called dilation, but you need to be careful because typically dilation keeps the proportion of the size and just shrinks it. Here we actually have a little bit of freedom in the way that we stretch it, because the proportion of the shape will change. So it is literally going to stretch it, and it will look taller or thinner or longer or stouter or whatever, right? And the way we do this is we use multiplication or division, but I mean multiplication by a fraction facilitates division anyway. So really just multiplication. And it only depends, of course, if it's outside or inside. And the size of the number that you're multiplying will make a difference to whether it's a stretch or a compression. Okay? Now, typically, only we worry about are the outside types of these things. And those give us all of our vertical stretching and compression. Okay? The number is multiplied outside of the function. A is times some function f of x. Okay? If that number a is bigger than 1 in size, then it's going to vertically stretch the shape. If the number a that you're multiplying is somewhere between 0 and 1, then it's going to vertically compress. Most of the shapes that you are accustomed to, and in fact all of the ones we're dealing with here in this algebra lecture today, don't have the freedom of the vertical and horizontal being just independent of each other. Okay? When you do the vertical stretching and compressing, for example, if you vertically compress, make the thing shorter, you will also get a horizontal widening as a consequence. Okay? It's just the way the shapes form themselves, the way the math works with the numbers. These two actions are not totally independent of each other. Okay? And vice versa. If you have a vertical stretching, then it will also have a sort of horizontal compression factor with it as well. Typically, that's why we only have to worry about doing just one of these two categories. I do put rare on the horizontal stuff, but you do need to know that it exists. If you have a number multiplied on the inside, then just as opposite logic would dictate, if the number's bigger than 1, it's a horizontal compression. Notice how those two go together, right? The number being bigger than 1, if I vertically stretch, it horizontally compresses as well. And then vice versa. If the number on the inside is in between 0 and 1, then you get a horizontal stretching, which is the same as a vertical compression. Like if you do this, it's going to want to do this at the same time. Okay? Now this particular category is difficult to graph on the fly. Okay? If you really need to demonstrate a stretch or a compress, there's two things that you can do, or both at the same time, to demonstrate that this has happened. One, you can graph an original shape and then graph the stretched or compressed shape along with it so that you can see physically the difference between them. Or two, you can start actually putting more work in, make it a 100% graph, plot points, make sure everything is actually in the placement it's supposed to be, and show that those dots are there. Now what I've done is both of those for this particular graph right here to demonstrate how you can show a stretch or a compression. The one that I have drawn in the black marker here is y equals x squared, okay? The red marker is y equals 4 times x squared, and the blue marker is y equals 1/4 x squared. Now, of course, 4 is bigger than 1 on the outside, so I should get a vertical stretch. And you'll notice when I actually computed the numbers, it is actually this and this. It would be taller, I just didn't finish drawing it out this way. But notice in just the distance that it takes to get to either 2 or -2 on the axis, it's already up at 16. Whereas the normal graph right here, y equals x squared, is still way down here at 4 when it's at 2. Okay? And then vice versa. 1/4 on the outside of x squared is between 0 and 1. So that should give you a vertical compression, and it does. You can see the blue graph is a lot shorter, but it's also wider. Okay? Now here's the example as to why we typically don't worry too much about the inside type of things. With all of the shapes that we're talking about here, they're all algebraically able to be simplified out of this category into the other category. For example, the only way I would get these same graphs using horizontal stretching and compressing is to have the number on the inside. Whoops, I misdrew this. This should be squared here. Okay? Notice 2x quantity squared is actually the same thing as 4x squared, right? But now the 2 is on the inside and is bigger than 1, so you get a horizontal compression. And notice the red graph is compressed horizontally. But it's the same thing. So I didn't actually need to worry about doing it this way. I could just do that one, you see. Same thing over here. The 1/2 times the x. 1/2 is between 0 and 1, would give me a horizontal stretch. Notice the blue graph is horizontally stretched. It is wider in the horizontal direction. Okay? But it's exactly the same calculation as 1/4 times the x squared. So there was, again, no reason to interpret it this way. I can just stick with my vertical stuff, and it's easier to see with these kinds of things. Okay? Any of these has that same connection. One way or another, you can find a way to convert a horizontal interaction of stretching and compressing into a vertical one with the shapes that we have here. Okay? But for example, later on, if you take trigonometry, things with sine and cosine don't have that luxury. We don't have a way of converting horizontal stretching and compressing to vertical. And when you're doing those trigonometric graphs, those actually have to be done independently, and you have to worry about both. So in that case, you actually move up to another type of graph where these two both matter separately. But with all the ones we're doing here, the normal algebra functions, these two types of things are going to be connected. So for the most part, you'll see that it'll mostly be the vertical stretching and compressing. But it does help you to know that the other one exists in case somebody tries to throw you a curveball. Okay? Let's look at a few of these. So here I have f of x equals -4 square root of x plus 1. Let's identify all of the pieces. The square root of x is the parent function. The plus 1 is going to be a shift left. The 4, just the 4, is going to be a vertical stretch. And the negative here is a vertical reflection. Notice the negative is not included in the number outside. It actually isn't. Look, these categories don't include negatives, and they shouldn't. The negatives only exist to give us reflections. Okay? Now, over here, I don't have any sort of reflection, but what I do have is a shift to the right And then this 3 right here, it used to be a 1. That's a multiplication by 3 over 1 to the whole fraction. So this is also a vertical stretch. All right. In this one right here, the 4 is multiplied by the x. All right. The 4 is multiplied by the x, which means it's one of these things, right? One of the horizontal phenomena. But watch this. If I factor this thing, 4 times x plus 2, like this, absolute values over multiplication can be split as long as you don't lose any of your important value. 4 is already a positive number. So I could just as easily write this like this, right? Technically what I did was I have the absolute value of 4, but the absolute value of 4 is just 4. And notice now I can treat this like a vertical stretch. Okay? This particular graph now is much easier to read. Also, it's easier to see the horizontal shift. Okay? Up here, it was not a shift of 8. That would not have worked. But here I can see it right away. This is a shift 2 to the left. This 4 right here is a vertical stretch. The negative right here is a vertical reflection. And the 3 right here is a shift up. And my absolute value, of course, is the parent function. And then lastly, over here, I just wanted to point out that just because something is a fraction does not mean it will necessarily fall into the category of the compression over here. 5 over 2, if you divide it out, is 2.5, which is bigger than 1. So this is actually also a vertical stretch of that function. Okay? Now over here, let's graph this guy out. So then what I want is a shift to the left by 1. That's going to be my new center point. And technically, my original square root function looks like this, right? I'm going to label this as square root of x. I know what you're thinking. Why did he do that? Remember, there's only one way, or there's only 2 ways really to show. And I'm not using a lot of accurate points. I'm trying to graph quick. So I'm going to show the original shape, and then this other one's going to need to be stretched. Okay, so I shift 1 to the left, and it's vertically reflected, and it's vertically stretched by 4. So it should be a lot taller than the other one. This will be f of x. Next, I'm going to shift 2 to the right, and I'm going to need a new guideline. So here I'll put my guideline at x equals 2. Notice I don't need a new guideline in the horizontal direction because I didn't do any sort of vertical shift up or down. But what I did get is a vertical stretch. So let's draw the original shape. Okay? The original shape is going to look kind of like this. And then let's get the stretched one. The stretched shape is going to be like this. Think about it like if I had 2 pieces of Velcro on the ground, right? Normally a stretch gives you this horizontal inner compression, right? In this particular case, the way the volcano function works is if I vertically stretch the 2 pieces of Velcro like this, think about it, it's going to rip more of the Velcro upward off of the bottom, like if it's taped down, right, and I stretch it upwards, it's going to go and rip away from the center a little bit like that. Okay? So in this case right here, the red graph is the actual graph that we're talking about, whereas the blue shape is the original volcano function. Okay? Here, with this one, since the absolute value function uses straight pieces, linear pieces, just two different directions like the V shape, I actually don't need to compare it to the original. I can count this one just like I would a slope. So watch this. I can do this where I'm shifting here. I'm shifting 3 up. 1, 2, 3 up. And then I'm shifting 2 left. So 1, 2. My new center is right here. Okay? I'm supposed to be vertically reflected facing down and with a slope of 4, you would say. So in other words, what I can do is count down 4. 1, 2, 3, and then here would be down 4. And then I'm going to go 1 in either direction. So that would be here and here, like that. And what this does is it gives me the accurate slope of the two line pieces with a slope of 4. Technically, it's positive 4 and negative 4 slopes because it's going in both directions. But let me do this one a lot better here. See, watch. It would be like this. Like this. Okay? So you can see it is squished horizontally, but it is stretched vertically. And it's facing down because of the negative. Over here, the vertical stretch 5/2 for x to the third, it's not shifted at all. It's not reflected at all. I just need something to give me some reference here. So then I'll draw the original. Right? That's sort of pretty good for the original here. Right? We'll just label it x cubed. And then a vertical stretch of this particular graph would simply make it look sort of skinnier, like this. Five over 2x cubed. Alrighty. I wanted to finish up with one more example of when you may have to do some of these effects without knowing an equation and just knowing an original graph. In the case like this, I have this original graph, which is just a connection, a piecewise function between several points. So I know that whenever I do any sort of translation, all of the pieces are going to remain linear, and I know all of the important points. If the shapes were not going to be linear, you would just have to make sure and figure out all of the important points. Like, for example, in a parabola, you'd want to know the vertex, the peak point, right? As long as you know all of those important points, then you can easily translate one of these graphs. In this case, those important points just happen to be the corners, right? So what I'm going to do is, since they're asking me to do these transformations of the function, I'm going to just convert each of these points using the transformations, and then I'll just connect them with the lines like I have the original graph here. Okay? So let's read what they want us to translate here. They want a shift to the left of 2. So what that means is each of my x values should get a subtraction of 2. So right here I should say minus 2, minus 2, minus 2, minus 2. Okay? Now the y is a little bit more complicated. It seems to have more pieces, right? With the y, I'm going to notice that, yes, I do have a shift up, but I don't want to do that shift up until after I've done both the vertical reflection and the vertical compression from the 1/2 there. Okay, so in each one of these, what I'm going to do first is I'm going to multiply times negative 1/2, and then after I've done that, I'm going to add the 1 that gives it the upshift. Okay, so in each one of these, I'm going to do times negative 1/2 and then add 1. Times negative 1/2, then add 1. Times negative 1/2, and then add 1. Okay, so let's find the new coordinates of these bad boys here. I'm going to have the point negative 5 because of the negative 3 minus 2. 4 times negative 1/2 is negative 2, plus 1 is negative 1. All right, here negative 1 minus 2 is negative 3. Negative 2 times negative 1/2 is 1, plus 1 is 2. Then here, I've got 2 minus 2 is 0. Negative 4 times negative 1/2 is 2, plus 1 is 3. Then right here, 4 minus 2 is 2. And then 2 times negative 1/2 is negative 1, plus 1 is 0. Okie dokie. So let's get these in. Negative 5, negative 1. So negative 5, negative 1. That'd be here-ish. Okay. Negative 3 and 2. That's right here. 0, 3 is here. And then 2, 0 is here. Okie dokie. Now, since there were straight lines before, they should still be, just somewhat shrunken because of the vertical compression. So I'm just going to connect the dots in order. Like so. Okay? So notice what we have is the same shape as before, but it's been reflected. You see this peak right here, right, is now up at the top. We still have this sort of corner right here. It's still right there. But it's been shifted to the left. It's been pulled over to the left. Okay? And it's not as tall as it used to be. It's been compressed. It's not as tall. It's been vertically compressed there. Okay? So I hope this section has helped you understand the way that we'll be interpreting a lot of equations and applications to functions and their graphs.